thing is which one? Is it this one? 61 to 72. So where is 61 to 72? Here it is. So can you see page 68 now of the slide?
Yes, sir.
Yes, sir.
Okay, very good. So last time, basically, we were discussing the theory of principal rings and how divisibility works in these rings. In particular, they are factorial. But there are many principal rings which are not fields. Fields are a very special case of principal rings. And I mean, that's the case when there are no irreducible elements, right? So we had this notation A heart, which consisted of elements which were non-zero, non-invertible. When A is a field, this A heart is empty. But we saw that when A is a principal ring, which is not a field, then this A heart, every element in A heart is the product of irreducible elements, and that in a unique fashion. Okay, so let's come to the simplest case of fields for a moment. And so we have a field K and two vector spaces E and F of finite dimensions M and N over this field K, and a K-linear map U from E to F. Okay. Such a map will have a certain rank R. We have defined it. Is the dimension of the image of U. So it's smaller than M and smaller than N as well. It's smaller than the minimum of M and N. Okay, so this is what is given to us. And the proposition says that I can find a basis B of E. This B is not a single element. It's a family of M elements, right, of the vector space E. And a basis C of F, which again is a family of N elements, N vectors in F. So whenever I have bases for the source and the target and a linear map between these two vector spaces, I get the matrix of this linear map in these bases. So the proposition says that I can find basis B and C of E and F such that the matrix of this linear map U is this particular, it looks like this, IR 0, 0, 0, where IR is the unit matrix of size R. It's the square matrix with ones along the diagonal and zeros off the diagonal. Square matrix of size R with ones along the diagonal and zeros outside the diagonal. And this kind of a form is called a block diagonal form. So this matrix here, it's not necessarily a square matrix, right? Because M and N may be different, but there are four. It has been split into 4 blocks. The first, the top left block is the identity matrix of size R, and the other matrices are zero matrices of the appropriate size, right? This matrix has, how many rows does it have? It has N rows and M columns, right? Right. Now, how do I prove this statement? This proof is easy. Everybody should be able to understand it. And it uses many of the things which we have covered, many of the properties of vector spaces that we have established. So I have this linear map U. It has a kernel and it has an image. The kernel is a subspace of E and the image is a subspace of F. In any case, subspaces of vector spaces always have supplements, right? Recall the definition of a supplement. It's a subspace such that when I take the sum of these two, I get the whole space and the intersection is the zero space. So take a supplement E1 of the kernel of U inside E. So this E will be written E1 direct sum the kernel of U, and take a supplement F of the image of U inside F. So F is going to be the direct sum of the image of U and F1. And I've written these numbers here, 47, 44, 40, 32, etc., to recall that, taking a supplement is not obvious. So we have established that supplements exist and being a etc., right? Now, when I restrict this mapping U to E1, it's a bijection with E modulo the kernel of U, and U, in fact, is a bijection from E modulo the kernel of U to the image of U, right? So keep this in mind. This isomorphism of U restricted to E with the image of U. So now I choose a basis B1 to BR of E1. What is the dimension of the kernel of U? So that was supposed to be, okay. The rank of the mapping is U, so the dimension of the image is R, but yes, and this E1 is isomorphic to the image of U, so the dimension of E1 is R. That's why I'm choosing a basis with R vectors in it, B1 to BR. Okay, let's choose such a basis of E1 and complete it to a basis of E. That's again something, I'm using some result here, which was proved on page 48, which says that if I have a subspace and a basis of the subspace, I can always find the basis of the whole space, of which this basis of the subspace is a part. Basis of a subspace can be completed to a basis of the whole space. Okay, so I completed to get a basis B of E. I wanted a basis B of E. I've now got this B. And I want a basis C of F. So first I take Ci, I going from 1 to R, to be just the image of Bi under U. Okay, so that's going to be a basis of the image of U. Why? Because I have this isomorphism with U is basically an isomorphism from E1 to the image of U, and I have a basis here. This isomorphism will take it to a basis here. So this C1 to CR is a basis of the image of U, and it too can be completed to a basis C of F1. That's it. You can check now that the matrix of the linear mapping U in these bases B and C, which I've constructed here, is this matrix. Okay. So that was easy. It used many properties of vector spaces, but it's not a very deep result. It's certainly a very useful result because it tells you what the matrix of an arbitrary linear map between vector spaces of finite dimensions looks like up to changing bases of the source and the target. Changing basis at the source amounts to multiplying the matrix on the right by an invertible matrix. Changing basis in the target amounts to multiplying the matrix of the linear mapping by an invertible matrix on the left. So this proposition here is essentially equivalent to the corollary, which says that if I have a matrix with n rows and m columns over a field K, and if the rank of the matrix is R, what is the rank of the matrix? It's the dimension of the subspace generated by the columns of that matrix. So, okay, so if I take a matrix of rank R, then there are invertible matrices P and Q of the appropriate size, because you cannot multiply a matrix n by m matrix on the left and right by matrices of arbitrary size. No, they have to have the appropriate size. To multiply this matrix on the left by a square matrix, it has to have size n, and to multiply it on the right by a square matrix, it has to have size m. In any case, what is being said is that there are invertible matrices P of size square matrices, or invertible, so square, of course, of size n and m respectively, such that PMQ is this matrix with IR here in the left upper block and zeros elsewhere. Okay, what we would like to be able to do is to find the analog of this theorem when your base ring is no longer a field as here, but a principal ring. Okay, so that's our next aim. We want to find the analog over a principal ring. So here is the here's the theorem. It says that if I have a principal ring A and a matrix over that ring with n rows and m columns, then there are invertible matrices P and Q of the appropriate size, such that P and Q is equal to D00, D. So it's a block diagonal matrix. But the upper left-hand row corner is no longer the identity matrix. It's a diagonal matrix here. D is the diagonal matrix D1 to DR, in which these DIs are non-zero. Okay, they're not equal to 1, not necessarily equal to 1, but at least they're non-zero, and each one divides the next one. Okay, so that's the best you can do. That's the best you can hope for when you have a principal ring, which is not a field. Let me repeat, because it's the statement which is important. If I have a matrix M with n rows and m columns, then I can find an invertible matrix P of size n and an invertible matrix Q of size m, such that P and Q is D00, D, where the top left-hand entry D is itself a diagonal matrix of size R, in which the diagonal entry is D1 to DR, are non-zero elements of your ring A, each one dividing the next. So this integer R is uniquely determined by M, and the elements Di are not uniquely determined, but they are determined up to associates. Okay, so for example, if one of them is 1, somebody else might say, no, it's a unit. 1 and units are associates, right? Or somebody finds that he can write one of his elements is 2, the corresponding element for somebody else might be -2. But that is the only kind of differences you expect. Otherwise, they are unique. So they are uniquely determined up to associates. Okay, so the statement, as I said, is very important. And for proving it, we will use this lemma, which is sort of a black box. I don't particularly like this lemma, but since it does what is needed, we will use it. I would have liked to give a more conceptual proof, but we have not developed the concepts which are required for that more conceptual proof. So this is going to be a more computational sort of proof. Okay, what does the lemma say? It says that whenever I have a principal ring A and a family of elements in A, then I can find a square matrix of size S. If I have S elements, I can find a square matrix M of size S, whose first row is A1 to AS, and whose determinant is the GCD of these AIs. See, GCD of these AIs is any generator of the ideal generated by these AIs, and that it's being claimed that you can always find a matrix M whose first row is this given row and whose determinant is the GCD of this first row. Okay, what about S equal to 1? Certainly true, because you don't need to, you just have one element and that itself is a matrix. So let's proceed by induction. By hypothesis, they're going to be a square matrix of size S minus 1, whose first row is A2, A3 up to AS, and whose determinant is the GCD of A2 to AS. I'm applying the induction hypothesis to the sequence of S minus 1 elements, A2 up to AS. Excuse me. Okay. So now the GCD of A1 to AS is of course going to be equal to the GCD of A1 and D, where D is the GCD of A2 to AS, right? And that can be written, that GCD can be written as A1x plus dy for some xy in A. So I get hold of this x and y, and it is being claimed that this matrix M, this very explicit matrix, does what is needed, where N is of course a matrix whose first row is A2 to AS and whose determinant is equal to the GCD of A2 to AS. So now this is just a matter of checking. It's a different question as to how somebody came up with this matrix, but as long as it does what we need, let's not ask too many questions. But I would expect you to check that the determinant of this matrix is actually equal to what? It should be equal to A1x plus dy, the determinant of this matrix, right? Yes. And the first row is obviously A1 to AS. Yeah. Okay. So this is the lemma we will use, and let's now come to the proof of this theorem. We have to find these matrices P and Q. Okay. So the first case we consider is when n is equal to 1. N is the number of rows. So you have just one row. And of course, you may assume that this row vector, or the row matrix, one should call it, is not 0. I mean, if it's 0, there's nothing to prove. Right? You just take the 0 matrix of the appropriate size, and the first row is the given one, and the determinant is equal to the GCD of the first row. So assume that n is not the 0 matrix, and put D equal to the GCD of x1 to xm. Because it's the GCD, there are elements A1 to AM such that D is the linear combination A1 x1 plus A2 x2 up to AM xm, right? What is the GCD of A1 to AM? It is, see, D divides x1 up to xm. So I can take it to the other side and I'll get 1 equal to A1 times something, etc., AM times something. so that 1 can be written as a linear combination of A1 to AM. So the GCD of A1 to AM is equal to 1. Now by the lemma, I can find an invertible matrix. Invertible because the determinant is equal to 1. The determinant is going to be equal to the GCD, which is 1. So it's invertible. So I can find an invertible matrix Q whose first column is the given sequence A1 to AM. In the lemma, we did it for rows, but the same thing will work for columns, right? So now I have an invertible square matrix whose first column is A1 to AM. And let's look at the matrix MQ. M is a row matrix here, X1 to Xm. Q is a square matrix, invertible, of the appropriate size. So the result is going to be a row matrix. And the first entry is D. The first entry is going to be, of course, A1 times X1 plus A2 times X2 plus AM, all the way up to AM times Xm, which is equal to D. So the first entry is D. And the other entries, let's call them B1 up to BM. But whatever these B's are, they are going to be divisible by D. Because it can be, because they're linear combinations of X1 to Xm, and any linear combination of X1 to Xm is divisible by the GCD. So these B1 to Bm are divisible by B. Now, there are these things called elementary operations, which correspond to multiplication by invertible matrices. Actually, multiplication by an invertible matrix, this elementary matrices we had introduced maybe on the last slide last time. So multiplication by an invertible elementary matrix on the left corresponds to an elementary row operation, and multiplying by an elementary matrix on the right corresponds to a column operation. What is a column operation? For example, it changes a column Ci, let's say column of index I, to this column plus alpha times some other column, jth column, let's say. I and j have to be different. So that's what an elementary column operation is. See, one of the things that you can do with column operations is to interchange two columns if you are willing to replace the sign in one of the columns. Okay? So for example, how do you do that? You have this matrix with columns, any number of columns, of which I've written only two, Ci and Cj. I and j are different. Now, I can apply a column operation and keep Ci as it is, and replace Cj by Ci plus Cj. Okay? And now I apply the column operation, which replaces the ith column by the ith column minus the jth column. The jth column is this now, Ci plus Cj. So I'll get minus Cj here and Ci plus Cj here. Then I can replace the jth column by the jth column plus the ith column. So the ith column remains the same, and the jth column becomes Ci plus Cj minus Cj, so it becomes Ci. See, Ci and Cj have got interchanged, but there's a minus sign here. So that applies to the rows as well. You know, I could have written anyway. So these column operations allow me to go from this matrix with B1 up to Bm to D0, 0, 0. How? Because these B1 to Bm are multiples of D, so I just subtract the appropriate multiple of D of the first column from this column, from the next column, and so on. From each of the columns, I subtract each of the columns 2 to m, I subtract the appropriate multiple of the first column. Then these entries will become 0. So from a matrix with first row x1 to xm, I've got a matrix, but by multiplying it on the right by some invertible matrices, I've got a matrix whose first row is D 0, 0, 0, etc. D in the first place and zeros elsewhere. So that proves the case D equal to 1 of the theorem. If D is, it's not the case for what? N equal to 1, yeah. Or is it N equal to 1? It's the case N equal to 1. There's one row, yeah. Okay. So how do we go from here to the general case? Let's come to the general case. So you have your matrix M, and by multiplying it on the right by the appropriate invertible matrices, we can make the first row D1 and zeros elsewhere, right? Now, just do exactly what you did to the first row to the first column now. So by multiplying the first column or the matrix, the whole matrix, by invertible matrices of the appropriate size on the left, I can make the first column look like D2 in the first is the first entry and zeros elsewhere. Okay. And when I do this, this new D2 that I get, that is the GCD of the first of the entries of the first column, right? This D1 was the GCD of the entries in the first row. And D1 is one of the entries in the first column. So this D2 will divide D1. Okay. So when I now do these column operations, or rather I perform these row operations to make the first column look like this, the first row gets destroyed. The shape, the structure of the first row gets destroyed. But you can restart and go back to the first row and do the appropriate column operations to make the first entry non-zero and the other entries equal to 0. So you modify your first row, then you go back to the first column, go back to the first row, etc. And in which the top left entry is going to be a sequence of numbers in which each divides the preceding one. D2 is a factor of D1, D3 is going to be a factor of D2, and so on. And we have seen that in a principal ring, this cannot go on. If you have an element D1, a factor D2 of D1, D3 of D1, etc., then they cannot be strictly dividing each other. At some point, you will keep on getting the same element. The same element will keep on getting repeated. It is at that time that your first row, or the first column maybe, will look like this, and this will be the GCD of the elements of the first column. Okay? So now you do the appropriate row operations to make the first column also of this shape, where you have one non-zero entry here and the rest of the entries are 0. So at this point, what do we get? We get a matrix where you have some element D in the top left-hand corner, zeros in the rest of the first row, zeros in the rest of the first column, and a matrix M1 in the rest of the place. Okay. Now, by the induction hypothesis, this M1 is of the form D1 0 0 0, and D1 itself is a diagonal matrix D2 to DR, and in which DIs divide DI plus 1, each one divides the next for all I from 2 to R. Okay, so we would believe that we are done, but we are not. We have got a matrix of the right shape with D's along the diagonal, and each one dividing the next, except that this, we don't know whether this D divides D2. Okay, this, so we have to do something in order to get some D which divides D2. So let's just look at the top left-hand corner. It looks like this for the time being. Now what is this? Why is it called R? R is for rows or something? Okay. Yeah. Okay, so let's perform this following row operation. You replace the first row by add the second row to the first row, you'll get this thing. And what's the lemma tell you? If you apply the lemma at this stage, you can replace this first row by this D1, D2, where D1 is the GCD of D and D2. GCD of the first row is going to be the GCD of D and D2. And by the lemma, I can replace it by D1, D2, and then I can get rid of D2 because, or it's going to be a multiple of D1. So I get a D1 here and I get some matrix here. Okay. But now when I've performed these operations, something else goes wrong. The point of the whole thing is that you repeat this process till this D1 starts dividing D2. And then you are done. Okay, so that was the existence part. We have shown that you can multiply the given matrix on the left and the right to bring it into that shape. But then there's this uniqueness part. Okay, so this uses things which we have not really done. You know, there are these minors of size k of this matrix and so on. So it can, I'm going to sort of skip this part. So those of you who are very keen can try to either read these notes or look it up in the PDF file. But this is basically what this theorem involves, right? Okay, so let me now go on to the slides which were meant for today. Okay, right. Can you see the new slides?
Yes.
Okay, good. Okay. So now I'm going to derive quite a few corollaries from this theorem which we have just established. Okay, the first corollary is the following. That when I have a principal ring A and a free A module of rank M, so it's basically A to the M, and a submodule of this free module. I don't know what this submodule looks like, right? I don't know whether it's free or not free or something. So what is being said is that there's a basis E1 to EM of the given free module. And a sequence of non-zero elements of your ring A, each dividing the next, such that D1, E1 up to Dn, En is a basis of N. So in particular, N will have to be a free module. Okay. So not only is it a free module, there's a basis of M such that some appropriate multiples of those basis elements are a basis of N, right? So let's proceed by induction on M. And the first thing we will prove is that N is actually finitely generated. Even that is not clear, right? This M is a free module of finite rank, but submodules, are they finitely generated? That requires proof. And here it is. So we can write M as A plus, so we'll proceed by induction. Suppose we have done it for free modules of rank M-1. Every submodule is finitely generated. Suppose we have proved this. And for M equal to 1, we know that it's true because submodules of the ring A itself are the same as ideals, and they are not only finitely generated, they are principal. That is the kind of ring that you are working with. So for M equal to 1, this is clear. And we now assume it to hold for free modules of rank M-1. And we are trying to prove it for a free module M, which is A direct sum A to the M-1. And so we take such a free module of rank M. Any free module of rank M will look like this, A direct sum A to the M-1. And we take M pi to be the first projection. It just takes a vector to its first coordinate. Now, what is the kernel of pi? The kernel of pi restricted to N. N is a submodule of M, right? The kernel of pi restricted to N is, of course, the same as the kernel of pi intersected with N. And the kernel of pi is A to the M-1. I mean, that pi is the first projection. So this kernel of pi restricted to N is finally generated by the induction hypothesis. Also, the image of N under pi is an ideal, so it's principal. And we have this exact sequence. The kernel of pi restricted to N, goes to the image of N. This is a short exact sequence in which we have proved that the image and the kernel are both finitely generated, so N has to be finitely generated. Okay, this refers back to slide number 20, where we prove this, that if in a short exact sequence, the kernel and the quotient are finally generated, then so is the middle thing. Okay. Now, we have to construct this basis of M. So first we choose an arbitrary basis Bi of N. And we cannot choose a basis for N, of course, because we don't yet know that N is free. But we can certainly choose a finite system of generators for N. So now let's consider the matrix whose columns are the coordinates of xj in the basis E. E is a basis of the module M, and basically, so this R should be this M, or maybe this M should be R, one of those things. They are equal, because these generators, we are expressing them, we are writing them as these column vectors of this matrix, right? Columns of this matrix. So multiply this matrix on the left by an invertible matrix amounts to changing the basis of the module M. And multiplying it on the right by an invertible matrix amounts to changing the system of generators of the submodule N. And after a while, we can, by appropriate multiplication on the left and right by invertible matrices, we can make this matrix of the shape that was there in the theorem, and therefore the result will follow from this theorem that I proved just a while ago. Okay, so that's the structure of submodules of a free module of finite rank over a principal ring. And here is the structure theorem for finitely generated modules over principal rings. So I'm given a principal ring A and a module M, which is finitely generated over A. And what this structure theorem says is that this module M uniquely determines a sequence of ideals, A1 contained in A2, etc., all the way up to AM. And this AM has to be distinct from A. So the module capital M uniquely determines this sequence of ideals such that M is isomorphic to A modulo A1, direct sum, and so on, up to A modulo AM. But of course, some of the AIs may be 0. These AIs are increasing, but we didn't say that A1 has to be non-zero or anything. A1 could be 0, and in fact, quite a few of the first few could be 0. The only requirement is that they should be an increasing sequence, and the last one should not be the whole of A. Okay, so how do we get this? So because M is finitely generated, it's a quotient of a free module of finite rank, right? You choose a system of generators for M and send the standard basis of A to the N to that system of generators, and you get a surjective A-linear map. Okay? So now the kernel of this map pi is going to be a submodule of A to the N. And what have we proved about submodules of free modules? We have proved that there's a basis of the free ambient module, and these integers d1 to dl, non-zero elements of the ring A, each dividing the next, such that d1 b1 all the way up to dl bl is a basis of this submodule kernel of pi. Kernel of pi is a submodule of A to the N, so I can find a basis b1 to bn of A to the N and elements d1 to dl, non-zero elements in A, such that d1 b1 all the way up to dl bl is a basis of the kernel of pi. Okay, so now that I know what the kernel of pi looks like, and I have this surjective map, M is going to be, of course, isomorphic to A to the N modulo the kernel. And as you can see, the kernel is generated by these things. So M is isomorphic to A modulo D1, direct sum all the way up to A modulo D, and then plus A to the N minus L. Why is this term there? Because this L, I mean, it's only it could be smaller than this N, right? Okay. So now what I was looking for are these ideals A1 to AM. So what do I take A1 up to AN minus L? I just take them to the zero ideal, N minus L is this thing here, this is the rank of this free part, as it's called. This is the torsion submodule of M, and I mean the rank of this module n minus L. I take the first n minus L ideals A to be the zero ideals. And the next one, I take it to be D sub L. You see, D sub L, in the sense of divisibility, it's divisible by all the previous ones. But in the sense of ideals, it's going to be smaller than the ideals generated by the other DIs. So I take this DLA, which is contained in D, and I call it D L. This indexing might not be correct. Yeah. Oh, yeah. So, no, that's correct. Yeah, the index is n minus L plus 1. It's generated by DL. And I take the final ideal AM to be the one generated by this D. What is it going to be? It's going to be generated by dr plus 1. Because what happens is some of these first few DIs might actually be units. In which case, I don't take those DIs. Because then the ideal is going to be the whole of A. So I start with DL, I go to DL minus 1, etc. I keep going down till I reach something which is a unit, and I don't take that unit. Okay? So I get this sequence of ideals A1, A up to AM. AM is distant from A because this dr plus 1 is not a unit. Okay. So now we have established the existence of these ideals AI, or this increasing sequence of ideals. We have to now prove uniqueness. So what is clear is that if I have M isomorphic to some other sequence of ideals, if M were isomorphic to, if there were another sequence of ideals B1 up to Bn, increasing and Bn distant from A, such that M is isomorphic to A modulo B1 all the way up to A modulo Bn, then this number n minus L, the corresponding rank of the free part, will have to be the same, because that is the rank of the free module obtained from M by going modulo the torsion. That's the torsion submodule of M. And we have proved that any two bases of a free module have to be equipotent. So this number, the rank is uniquely determined. So all we have to do is to check that if I have elements D1 up to DT on the one hand, and even up to ES on the other, in this set A heart, which was, you see, non-zero elements of A minus the units of A. If I have such sequences with the property that the module T defined as A modulo A1 direct sum all the way up to A modulo DT is isomorphic to A modulo E1 all the way up to A modulo ES, then I have to show that this T is equal to S, and each DI is actually associated to the corresponding EI. Okay, this is what we need to prove now. Okay, so so this will follow from some of the theorems which we had, some of the propositions about monogeneous modules over principal rings which we had established earlier. So here is one small lemma. For example, if I have an irreducible element in my ring A and some element E, then I have E modulo P, E modulo EA, and from there I can go to A modulo EA modulo P times A modulo EA, And the claim is that this is 0 if the GCD of P and E is equal to 1, and it's just A modulo PA if the GCD of P and E is equal to P. Of course, the GCD of P and E can be either just 1 or P, because P is irreducible. Okay? So this lemma is very easy. I leave it to you. I mean, it must be a consequence of some of the things which we had proved earlier. So now I have these two modules T and S, and they are isomorphic by hypothesis, and I have to prove that this little t is equal to little s, and the di's are associates of the ei's. So let's look at an irreducible divisor P of D1. Why does D1 have an irreducible divisor? Because it's a non-zero, non-unit element of a principal ring. We have proved that every such thing has an irreducible divisor. Take some such divisor P. So A modulo PA is going to be a field, because in a principal ring, an irreducible element generates a maximal ideal. So what is the dimension of T modulo PT over the field A modulo PA? It's equal to T. It's equal to the number of summons here. But how about the dimension of S modulo PS over A modulo PA? This, by definition, by this lemma, is equal to the number of indices J, such that the GCD of P and EJ is equal to P. Because those are the only ones which contribute. The others don't contribute. The quotient is 0. Okay? So the number of J's has to be at least equal to T. That means that S is at least T. I mean, if there aren't T elements here, if there are less than T elements here, I can't choose T elements from less than T elements. So in order for the number of such J to be T, this S has to be greater than T. And of course, I could reverse the argument, and it's completely symmetric. So by symmetry, I get S equal to T. Okay, now let's look at D1T. Again, some of the results which we had proved earlier will tell you that D1T is isomorphic to A modulo D2 D1 inverse A. The direct sum all the way up to DT D1 inverse A. Okay, that's one thing. How about D1S? That also we had shown that it's going to be A modulo E1 G1 inverse A all the way up to A modulo ET GT inverse, where GI is the GCD of D1 and EI. Okay. Now let's look at the number of non-zero summons in this and in this. So then they have to be the same. But this has one term less than this one, right? This starts only at 2 and this starts at 1. T is equal to S, we have already established. So the number, because these two have to have the same number of non-zero summons, we conclude that this E1 G1 inverse has to be invertible. This first one has to be trivial. So E1 divides D1, and therefore E1 is associated to D1 by symmetry. And therefore we get and the proof is over by induction. Okay. Okay, since I have only 1 minute left for the remaining 5 or 6 slides, let me go through it quickly. So one of the corollaries is that over a principal ring, a finally generated module is free if and only if its torsion subgroup is trivial. Okay, that's what we have seen. Any finally generated module looks like a free module. Direct sum, its torsion submodule, and the torsion submodule can never, if it's non-trivial, it'll have elements which are not free. So the whole module is free if and only if that there are no non-zero elements in the torsion subgroup. Okay. And the second corollary is when you apply the theorem to the ring Z, which of course is a principal ring, the first example of a principal ring. And Z modules are really the same thing as commutative groups. So it says that finitely generated commutative, any finitely generated commutative group is isomorphic to Z to the R, direct sum Z modulo D1, direct sum all the way up to Z modulo dt, where for uniquely determined integers R and T, positive integers, where these di's are strictly greater than 1, and each one divides the next. So this, if your finitely generated module is given, it uniquely determines two natural numbers R and T, and T strictly, not just strictly positive, but strictly greater than 1 integers di, each dividing the next, such that that commutative group, finitely generated commutative group, the given one is isomorphic to this direct sum. Okay, so examples of such groups are furnished by, for example, Z modulo P to the N Z star. And for this, you can show that it's actually cyclic of this order. Similarly, this is true only if P is odd, the prime P is odd. For the prime 2, it's actually this direct sum of this group plus minus 1 of order 2 and a cyclic group of order 2 to the n minus 2. Z modulo 2 to the n is isomorphic to plus minus 1 direct sum, a cyclic group of order 2 to the n minus 2. And you can actually take the cyclic group generated by the number 5. Okay. So I'll skip this duality thing because I don't have the time. Yeah. Another important example of a principal ring is the ring of polynomials over a field. And so how do you apply it to the polynomial ring? So that arises when, for example, if you have a ring, any commutative ring A and an A module E and an endomorphism of this A module, then this E can be viewed as a module E sub U over the polynomial ring AX. How do I multiply a polynomial with a vector X? X is a vector in the X is an element of the module and P is a polynomial in this ring. So I can evaluate this polynomial at the endomorphism U and then apply, that's PU is an endomorphism of the module E, and I can evaluate it at the element X. And that makes this E into a module over AX. Okay, so submodules, it should be not subspaces, submodules of E, which are stable under F, in the sense that U of F is contained in F, correspond to submodules for the AX module structure of the module AU, EU, and so on. So all this is interesting, especially when this A is a field, because in that case, KX is a principal ring, and E will have finite dimension over K if and only if this EU is a torsion module over this principal ring KX. And we know what torsion modules over principal rings look like. They determine a sequence of elements P1 to Pt here. I can make them unique. They were determined only up to associates, but here I can make them unique by taking these polynomials, by requiring these polynomials to be monic. So they are of strictly positive degree, because if they have degree 0, then it's constant, and those are units, and there's no need. The units will. There's no need to take them into account. So here, what I'll get is that EU is isomorphic to kx modulo P1 direct sum all the way up to kx modulo PT. Okay, so when you translate it back for the K space E, what it means is that you can find U stable subspaces Fi such that E is the direct sum of F1 all the way up to Ft, and each Fi is cyclic in the sense that there's a vector xi in Fi whose images by the powers of U generate Fi. To see this, you just need to take xi to be the image of 1 in kx modulo Pi. You know, this Fi is just the space kx modulo Pi. Yeah, here it is. So I'll take maybe just 2 more minutes to tell you what the structure of cyclic modules is. So I have a field K, a polynomial P, which is monic of degree strictly positive. And I look at E, which is kx modulo P. If P looks like this, then I get an endomorphism of this K space E, which sends a vector x to x times x. This capital X times little x. Why can I multiply these two things? Because of, after all, this little x is in this quotient, and I can multiply by elements of the ring Kx. So what one can check is that what is x here? So this x was an arbitrary element of E, but now I'm taking x to be the image of the element 1. And I'm claiming that x, ux, all the way up to u to the r minus 1x, this r is 1 less than the degree of the monic polynomial. The r minus 1 is 1 less than the degree of the monic polynomial. So these things, this can be written as u to the 0 of x, u1 of x, all the way up to u r minus 1 of x. These r vectors form a k basis of E, and the matrix of U in this basis, U is after all an endomorphism, so it has to have a matrix in any basis of the vector space. The matrix in this basis is this matrix, where you have ones just below the diagonal. You have, what have I done? You have ones just below the diagonal. You have zeros elsewhere, except in the last column, which consists of the coefficients of the polynomial P, but affected with the sign minus. Okay, minus A0, minus A1. These alpha should be A's all the way up to minus A R minus 1. Okay. So this is kind of completely obvious. You just need to check them. And finally, so that's what happens. So this matrix, by the way, is called the companion matrix of the polynomial P. It's completely determined by the polynomial. You have ones just below the diagonal, and the coefficients of the polynomial here in the last column with the sign minus. So this says that if I'm given an endomorphism U, then I can choose a basis in which the matrix looks like this, where these polynomials, these CPIs, are the companion matrices of certain polynomials Pi, and there are 3 of them, monic, strictly positive degree, each dividing the next and they're completely determined by U. That is, that follows from the structure theorem for finitely generated torsion modules over this principal ring Kx applied to this. You make this E into a Kx module by making capital X act through this endomorphism U, and then it's a torsion module over this Kx, so it has to have that structure and so on, right? Okay, so this Jordan matrices, okay, let me finish here. This is actually the last slide, I'm sorry, but here it is. So I again have a field K, an element alpha in the field K. I take P to be this polynomial, x minus alpha to the power E for some integer E. Then I look at this K space, which is Kx modulo this polynomial P, right? X minus alpha to the power E. And I have the corresponding endomorphism of this K space. Let's call it U. It's basically multiplication by this indeterminate X. And the claim is that there is a basis of the K space E in which the matrix of the endomorphism U has this shape. It has alphas along the diagonal, alpha being the same alpha which is used to define this P, and ones just below the diagonal. Okay, so he says let Y be the image of X. That's obviously incorrect. Let Y in E be the image of 1 in Kx. And then we claim that this Y, X minus alpha times Y, X minus alpha to the E minus 1 times Y, etc., they form a K basis of E. And then in this basis, the matrix of the endomorphism U is this matrix. So there's a small checking here, and that's it. I wanted to tell you some story about some, recent applications of linear algebra, but I don't really have the time. Maybe I'll write it up in the notes and you can read it. Or I can send you some links to some material where you'll find what I wanted to share with you. So that's it. That's the end of the last lecture. And
thank you, sir.
Yeah. Are there any questions?
Good evening, sir.
Yes.
I have one question. It's not somehow related to Dalawat so may I ask?
Well, I'm sorry, I can't hear a word of what you are saying. So can you send me an email, or can you try repeating your question? Hello?
Hello, sir. Hello.
Yes.
Sir, can you suggest some reference book?
Oh, well, this is such a standard subject that, I mean, it's got, well, I mean, many people read this book by somebody called Halmos. It's called Finite Dimensional Vector Spaces. Most of the initial material which I have presented here has been taken from a book by Nicolas Bourbaki. It's chapter 2 of their book on algebra. The chapter is called Linear Algebra. And he does it in a very sort of coordinate-free manner, in the most natural possible way. But that might not be perhaps the best resource if you are coming across this material for the first time. But there are so many standard books on linear algebra. I think there's a book by Manin and somebody else as well. There's a book by Shafarevich, perhaps. And I'm sure, well, You see, another thing which you can try to do these days, instead of looking for books, you try to look for online notes by various people. These days, people write up their lectures and put them up on their own website. Or there's also the American Mathematical Society on its website has a section where it shares notes of various courses and lectures and so on. So there are so many resources. Of course, some of them are of poor quality and you have to exercise your judgment. But there are many resources, yes.
Okay, sir. Thank you.
Yeah. Other questions? Dr. Gupta.
Yes, sir.
Yeah.
So if you have no question, then claps for Professor Dalawat.
Thank you.
So on behalf of organizers and participants, I want to thank you for your insightful presentation. Although we couldn't meet personally, but sir tried to interact as much as possible. I feel that participants will be benefited by your lectures and materials in future, and they really enjoyed your presentation. We also appreciate you making time in your busy schedule, as we are aware that you have lectures in different programs from tomorrow. As a speaker, your expertise is of great value to the workshop, and we hope that you will be able to join us again in future. Your contribution means a lot to make this workshop successful. Thank you so much, sir.
Thank you. Thank you for listening. What do you have in the background? That's your house or something?
No, sir, it is imaginary background of Google Meet.
Okay. For my background is also imaginary.
Yes, sir.
Yes, sir.
Okay. Right. Bye-bye.
Okay, bye, sir.